Welcome everyone to our webinar, 10 Things You Probably Never Knew About GD&T. I am Rose Kopsha from Tooling U-SME and your moderator for today's session. For over 90 years, Tooling U-SME has promoted the advancement of manufacturing by supporting new technology in industry and the development of its workforce to sustain manufacturing. Before we start our webinar today, you will notice on your screen a Q&A box that you can use to submit questions or comments. And you'll also see our speaker's bio on there. We will try to have time at the end for discussion on our topic. A recording of today's session will be made available on our website at learn.toolingu.com. At this time, I would like to introduce our highly acclaimed GD&T expert, Mike Lewis.
Good afternoon, everyone. Welcome back. We did a webinar a few months ago, and that was well received, so we got another one going on. And so 10 things you probably never knew. Hopefully you do know some of them, but if not, I'm going to share with you a quick overview of 10 things you probably didn't know. There are probably 10 more things you probably don't know, because as I was doing this, I found a whole bunch more than 10. And so we may, in the future, do another one for another 10 to pick up the stuff that I wasn't able to put into this one. So a couple things before we get started, and that is the slides are pretty busy. There's a lot of material. I got 50 slides. I'm trying to get through them in 50 minutes so that we can have 5 to 10 minutes for question and answer. Understand that I can't see the questions when I'm presenting, and so Rose and Angela are going to be monitoring those questions via chat, and that's kind of how that's going to work. In the slides, look for keywords. Now, if any of you want copies of these slides, you can get them one of two ways. You can contact Rose or Angela that are hosting this with Tooling U-SME, or you can take screenshots. I do that all the time. I'm sure you guys are going to do that too. And so you can do that. But whenever you get a copy of this presentation, if that's what your goal is, look for the keywords. GD&T is really big on using words the right way, the right words for the right meaning. And so I've tried to circle those key words that jump off the page that should be getting your attention when we get there. So I'll be trying to point you towards keywords that I haven't circled. Otherwise, I've already circled them or underlined them, or I got arrows pointing all over the place. I'm kind of anal with arrows. And a couple of other things. I have pulled a lot of the graphics, not all of them, from several different sources. The one where the majority of the figures are taken from is a book by Alex Krulikowski called Fundamentals of Geometric Dimensioning and Tolerancing, 3rd edition, not 2nd, 3rd edition, and it looks like this. And here's where you'd want to take a screenshot real quick, because that's the book. I recommend it. I use it in all my teaching. And then some of the stuff is so weird that the textbook that Alex Krulikowski put out doesn't even have it in there. You will find some of those things in the ASME Y 14.5 standard, the 2018 version of the standard. And so those pages will be appropriately marked, and all other graphics, if they have a figure number and a page number, like this page right here. I'm trying to advance the, oh, there it is. Like this graphic right here, it's the first one. Notice that the textbook page number is in the lower left corner, okay? That's the Alex Krulikowski book. Here's the only time I am going to reference that book, but all the other times you'll find these graphics in that book at that page number, okay? And so, slide 1. This is our intro to datums, and this course is really beyond an advanced course. This is it's a step beyond advanced. It's into some of the really weird stuff. And so that's why I titled it the way I did. This is not so weird. This is what everyone should already know. This is your basic primary, secondary, tertiary flat datums. And it's just a quick reminder that says, this is what we should know, and here's where we need to go. We're going to be using datums and unusual features for datums in the following slides. This is here because some of the things that have changed in the ASME standard from 2009 to 2018 is the definition of how to deal with unstable datum surfaces. Okay, and here are the ways that we deal with it. So we have a part that rocks, and we have two choices. We can use an algorithm if we're using a CMM, or we can use a shim stock on this to balance out the rockiness, so that if we're on a granite table and we're using an open setup, or we're using standard measuring equipment that I will be abbreviating SME, has nothing to do with tooling U-SME. It's SME, standard measuring equipment. If we're on a granite table and we're going to use a dial indicator, we need to use shim stock to keep this thing from rocking. And what we do is we balance it. We do not push it all one way or all the other way. We balance it, shim it, and go from there. Now, if it's using a CMM, use the algorithm that's built into the CMM for parts that are rocking. And it will look at your part, and however you balance it, you've got to hold it where it is on the granite table under the CMM, and the CMM will take that rockiness and that out of flatness into consideration in an algorithm. So just a point of something new, something different, because in the previous versions, we were supposed to rock the part all one way, and now we balance. Okay, here's a machined block that I threw in here, and it's got 4 holes. Very, very simple. There's, nothing else in the training that's that simple, but this is here because we're going to drill those 4 holes in a mill vise. And one of the things I'm trying to get across to everybody with this graphic is we have the block that's shown in the lower left corner that we're going to go drill 4 holes in, and we're going to do it in a mill vise on a milling machine, whether it's manual or it's programmed, whatever. We still have to hold the block in a vise. Somehow we have to hold it, and we need to locate it to and against datum B. Notice right here, datum B. Okay, so why are we putting the dial indicator on the one vise of the mill vise? And that's because mill vices are really weird in that the solid jaw, we have the 2 jaws in the mill vise, the solid jaw, the movable jaw. The solid jaw is perfectly anchored and is to be lined up to the travel on the table. That's how we line up a mill vise on a table. And then after we do that, we put our part in, but we always put datum B against the solid jaw. You would never put datum B against the movable jaw, because the movable jaw floats, and it's going to follow wherever the part goes, or however unparalleled the sides are. So we always want to make sure, and the purpose of this graphic is to make sure you always put datum B against the solid jaw of the mill vise. Okay? And this is just one other example of how the application and use of datums and GD&T on even simple parts has a profound impact in the way that we set the parts up and produce them in manufacturing. Okay, some more datum stuff. I grouped all the datum stuff together. And basically we got this part on the left, and it's got some areas here that got the cross hatching. That was area B. This is area A. And notice area A is a line. It's a line all the way around that. And datum B is an area all the way around that diameter. So that takes you then to the view on the right, and you see that we're going to grab datum A area with a chuck of sorts or a collet, and we're going to make sure that we grab only the area that's identified with the crosshatch in the left, and we will only then grab the area that is datum A, which is a circle with something that's a collet. A collet is a tapered kind of thing that grabs a diameter, and it makes line contact. It does not make area contact. So on the right, the chuck will make area contact. On the left, the collet will make line contact. And these two both are simultaneously grabbing the part, and that is what creates datum A dash B. Okay? These are some weird things to do and some weird ways to do it, and that's why it's in this lesson. And here's another one. We have this part on the left, and we have datum A is on the face of the part, and datum B is on the OD of that boss that sticks out. And according to the feature control frame that's used on that part, datum A is primary, which means we make 3-point contact on datum A. And notice right here, that face that is datum A is making 3-point contact on the collet, where the diameter is not making 3-point contact. It's only making like 1-point contact. And so understand datum A being primary is 3 points, datum B secondary is 1 or maybe 2 points. But if we reverse these, then we would say that B was primary, and then we would grab on all of datum B in the area that's crosshatched and make 1-point contact then on the face of datum A. So understanding these datums can be on the same part and they can be conflicting. We could even have holes in this part, some of which are located primary to datum B and then secondary to A, and other holes primary to A and secondary to B. So it's really the part geometry and the way it functions. Here's some other weird stuff with datums. Notice that we have datum A is established with 3-point contact. They're on 2 different levels, and that's the weird part. Here they are again. We got 1, 2, and 3. Can we do this? And if we do, how do you call it out? Well, you see how we got these A's here? You can do these things. Or you can even make datum A off the part a certain basic distance to all 3 points. So this is a weird application. It's on page 178 of the book. One last thing on datums. This is kind of an oddball one. We've got this part and it's got a datum A primary, datum BC is secondary, and datum A is right here, and it's identified as just the plane, but datum B is all over the part. We have datum B as this line and that line where they contact that spherical radius or that radius on the end of the part. And it's obtained, if you look on the right in the graphic, after we contact points C1 and C2, we use those points to push the part into the nested tool or the next nested inspection fixture that picks up the contact at B1 and B2. And it's probably not going to be line contact. It's probably going to be point contact. So we're moving on. We're done with datums for the most part. Rule 1 is size controls form. But other things that we need to talk about are what else does it control? Rule 1, size controls and contains form. And I'll show you more what contains mean. Versus what we don't want to do, and that is we don't want to use Rule 1. Rule 1 says by default, anytime you have something of size, you automatically control and contain the form of that size. Versus if I have size, but I don't want to control or contain form, then I can have this called the independency concept. And the independency concept, and I've got some examples, is coming up. Okay, there's a lot of stuff on here. Rule 1 only applies to regular features of size, not irregular. So what's regular and irregular? It's coming up in a few slides. Rule 1 does not control location, orientation, or the relationship between other features of size. It doesn't control profile, run out. It only controls form. Only form. Okay? There are two exceptions to Rule 1, and that is if the parts are made out of like rubber, okay? Because they're too flimsy. And if we're buying raw material from a supplier and we want to make sure that the material is real straight, okay? Well, the straightness of that raw material is controlled not with GD&T, it's controlled by the standards and the requirements by the supplier of the raw material. They will provide material that's straight, round, and whatever it's required to be in their material delivery requirements. Okay? We don't use GD&T for that. And because of that, Rule 1 does not apply to bar stock. Okay? There are 3 ways to override Rule 1. And we're not going to go through the first 2. That might be something for, the advanced, the next 10 things. Anytime we use straightness tolerance applied to a feature of size, to a regular feature of size, Rule 1 doesn't apply. It also doesn't apply to flatness tolerance to a feature of size. And if you took the last GD&T seminar, the webinar, this stuff is in that chart that I gave everybody that I made sure you all got a chance to see. It's in that chart. Go look at it there. Right now, I really want to talk about the independency symbol and its application to a regular feature of size. But before we do, a quick reminder. We're going to talk about MMC, LMC. MMC means maximum material condition. That means it is the largest shaft, the smallest hole. Okay? In the upper left corner of this figure, we have a round part. And its MMC is the largest shaft. The MMC is 12.3. It is not 11.7. Okay? The largest shaft, the smallest hole. And so we look at the hole in the lower left, and we see that the MMC is 11.7. So the MMC of the shaft is 12.3. The MMC of the hole is 11.7. We have to remember that. We have to know that because I'm going to keep talking about it like you do know it. Now the figure on the right is LMC. That's the opposite of maximum material condition. And I'm not going to talk much about LMC because it just gets the things confused with largest shaft, smallest hole. Just remember, MMC, largest shaft, smallest hole. When I'm doing this training in real life and, it's like a 3-day training, I repeat that about a dozen times and people still get it wrong. So you will get this wrong if you don't remember. Largest shaft, smallest hole. Okay. Rule 1, size controls form. It also contains form, like I said in the previous slide. So we're going to look at the left, and we're going to see that Rule 1 applies to this shaft. What's the MMC of the shaft? It's 10.8. Okay, 10.8 is the boundary of perfect form at MMC, which means when the part is actually at 10.8, it has to be perfectly straight and perfectly round. Perfect. I'm only ever allowed some out of straightness or out of roundness on the pin if I go away from MMC. So as the OD of the part gets smaller, the part can get more out of round and it can become more curved, but only to the degree within the perfect form, the boundary of perfect form at MMC. Okay, that means if the part is at 10.6, it can be only out of round and or really or out of straightness 2/10 of a millimeter. Otherwise, I'll violate the boundary of perfect form at MMC. Okay, on the right, I got a part with a hole in it, and the hole is 14.6 to 14.0. What's MMC? It's the smallest hole. It's 14.0. The MMC it creates a boundary of perfect form at MMC, which means if the hole is at 14 millimeters, actually, it's got to be perfectly shaped and have perfect form. Okay? It means it can't be out of round, it can't be curved or out of straightness. It has to have perfect form only when it's at 14 millimeters. As we deviate from 14 millimeters and the hole gets bigger towards 14.6, then it's allowed to go out of round and out of straight only within the perfect form at MMC boundary. So you got to remember, this is an assumption. It's rule one. You always have to know it. You always have to apply it. And that's why it's so important. So now that you know this, we're going to say what rule one does not control. And I already told you, it doesn't control any of this stuff. It only controls form. Here's our part. Notice the oval in the top. Here's my diameter, 10 millimeters plus or minus 0.2. And notice the eye in a circle. That's kind of new. The eye in the circle says, warning, warning, we do not have to comply with rule one. We do not have to stay within the boundary of perfect form at MMC. That means that dimension of size doesn't control my roundness or it doesn't control my straightness. Not at all. And the reason that it doesn't is because that eye in the circle says it doesn't. But understand, if you use the independency symbol and you say it no longer has to comply with rule one, now it can be out of round any amount or out of straightness any amount unless you add a straightness or a roundness tolerance to that surface and that diameter. And if you do, it should be more than the 0.2 millimeter. It would probably be 0.3, 0.4, 0.5. And it would say that the most important thing on that pin is the size, not the straightness nor the roundness. And so I'm giving more relaxation to the roundness and straightness to the part by using the independency concept. But if that roundness and straightness of 0.2 millimeters is good, I would take the eye out. And rule one says, now, perfect form at MMC, the 0.2 is controlling straightness and flatness as I deviate away from MMC. So that's why we had to talk about this, so we could understand the independency concept. Okay, so we're going to keep going. Regular and irregular features of size. They look like this. These are regular features of size, and regular features of size are opposed or partially opposed. That means everything on here is opposed. You can measure it with a micrometer, that kind of stuff. This, you cannot, okay? You've got the 20 millimeter dimension, and there's no way to use a pair of micrometers to measure that. So this is an irregular feature of size, and an irregular feature of size does not require us to abide by Rule 1. So no Rule 1 applies to irregular features of size, but they do apply to regular features of size. Now you know. Okay, we already talked about that. Pitch diameter rule. What we show here is a drawing on the bottom. It's a partial drawing. It's got some threads. And the reason for this is to tell you that if you call out threads and you don't use major or minor diameter, the default is that you will automatically be required to measure the location of those threads to the pitch cylinder or the pitch diameter. And it's not just for threads, it's for gears, splines, anything with a pitch cylinder or a pitch diameter, including threads. And so this is called the pitch diameter rule. Now, why is this important? Because 99% of the people out there that are putting threads on drawings don't know that they have the option to add major or minor diameter to the call out. I do, and I put it on my call out. Notice in the red box, it says major diameter. Now, because I'm making this part all in one setup on the lathe, I'm cutting the major diameter and all of the other diameters, including the datum diameter, which is B, which you can't see because it's kind of off the page. I'm cutting them all in the same setup. So I know those threads are going to be true to the same center line as datum B, so I'm going to measure the thread locations to the major diameter, not the pitch diameter. And it takes like, a tenth of the time to measure the major diameter, number one, and then to figure out the location of the major diameter back to datum B. So I use this often. And when you do, that's how you would call it out. And if you have a threaded hole you're applying threads to, and you don't call out minor diameter, if you leave it at pitch diameter, which is you put nothing on the drawing for the major or minor diameter, the default is you get pitch, then you got to use like the tool on the left that threads down inside the threaded hole. It's a self-centering, spring-loaded gauge that you can thread down in the hole that picks up the pitch diameter that you can sweep the OD that's sticking up on the right end of that pin to figure out where the center line of the pitch cylinder is on the hole. And these are very, very expensive. And so, the recommendation is don't use pitch diameter on either OD or ID threads if you can accomplish the same major thing with the minor diameter on the ID threads and major diameter on OD threads. This is just for your info, your reference, so that you all get a feeling and an understanding of what a major, minor, and a pitch diameter is on an external thread on the left and an internal thread on the right. Okay, everything you wanted to know about threads. So that's really there, not so we talk about it, so that it answers your question, what the heck is a major, minor, and pitch diameter? Go and no-go and functional gauges. We're doing pretty good. I'm not sure what page we're on, but we're doing pretty good. Okay, so first of all, gauges fall into two categories. We have size gauges and location gauges. And before we can even talk about this, what I need to share with you all is when you have a production part that you're producing and you're making it, you're checking it, you're doing all these things, the things that we check first of all is always size. If we have a pattern of holes, we always check the size of the holes. And we can do that with go and no-go gauges, thread gauges or plug gauges. And so in that case, we're using go and no-go gauges to check for size, but not location. Now, if we want to check the location of the 4 holes in our block that we showed just a little bit ago, we would use go no-go gauges to check the sizes of the holes. And then we would have a functional gauge, which I've identified here in the second bulleted page. A functional gauge checks the location of the holes as well as a little bit of the size. And so when we want to check size, we think go and no go. But if we want to check location, we have to think functional gauge. Now, I have pictures and examples of them, but we have to understand right out of the chute, these are not the same things. Go and no-go gauges are much cheaper and easier to use, and they're used for only checking size during production on the line while we're making parts. Functional gauges can be used on the line, but they're typically used after we're done making the part, when all the holes are already in it and all the datums are done and all that kind of stuff. And then we have this gauge, this functional gauge that we put the part on. And if it goes on the functional gauge, excuse me, if it goes on the functional gauge, the part is good. If it does not go on to the functional gauge, the part's bad. And gauges are wonderful things, but gauges fall into the category broadly of attribute data. Attribute data says, I don't know what the size is, but the go didn't go, or the no-go did go, and it failed. Or the functional gauge didn't go on, and I don't know what's going on, but it didn't go on. I'm rejecting it because the size gauges didn't work, the functional gauges didn't work. And that's because these things are categorized as attribute data. They don't tell you any sizes. They just tell you if it's good or bad. They have their applications in high volume production. But in low volume production, we may want to use actual micrometers or depth gauges or CMMs. CMMs are actually collecting data that we plug into the CMM. We tell the CMM what the diameter should be, and then we go put the probe down in the hole, collect points, and the CMM figures out the size, and it compares the points it gathered to what the size is that you entered into the CMM that it's supposed to be, and it says, oh, it's a good part, or it's a bad hole. And so we have attribute data with go, no-go gauges and functional gauges, and we have variable data with a micrometer and a CMM. We have to understand the differences between the kinds of gauges and the things these gauges will check. Okay? Now, functional gauges are only used when we are calling out MMC or LMC on the drawings. Okay? If you have a drawing and you don't want to use MMC or LMC, and you don't put anything on, you don't put any material condition modifier on the feature control frame, it's automatically, by Rule 2, which I told you we were going to talk about, Rule 2 says it's automatically regardless of feature size, which means it doesn't matter if it's at MMC or LMC, whatever the size is, regardless of its size, it has to meet this true position. You don't get bonus tolerance with RFS, which is regardless of feature size. And the biggest is you don't get to use functional gauging if it says RFS. Now, the sad part is it doesn't even really say RFS. It only has to say not MMC or M in a circle or L in a circle. Because if you screwed up and you forgot the M in the circle, but you wanted it to be MMC, too bad, you got RFS. And if you put RFS on the drawing, or if it's even assumed, you're not allowed to use functional gauges. So if your production is going to be based on using functional gauges, you better make sure all of your feature control frames that have material condition modifiers and features of size all have MMC. It's a big, big deal. I can't tell you how big of a deal it is. Okay, these are what go gauges look like. You've probably already seen them. If you want more information about gauging, there's another separate ASME standard. I have it. It's very well done. It's kind of expensive, but they all are. And then this is an example of a part with a go and a no go gauge. If this is our part and the diameter is 10.8 to 10.2, we make a gauge that is the largest shaft. Remember, at its MMC, the MMC is 10.8. Here's 10.8. There's my boundary of perfect form at MMC. That's my gauge diameter, 10.8. That means a pin at 10.2 will go through there, even if it's bent up to 6/10 of a millimeter. If it's bent more than 6/10, it won't go through that. That means it'll fail the go gauge, and that's what we want. If it's out around more than 6/10 of a millimeter, it won't go through that go gauge, because the go gauge is perfect form at MMC. Now, we checked the diameter of the gauge, or of the material, at its high side. Now we check the material at its low side, 10.2. Now, would a 10.1 diameter gauge go through that go gauge? And the answer is yes, it would. So in order to properly use go and no go gauging, you got to use both the go and the no go gauge on the same part, one right after the other. Because if the part diameter is really 10.1, it will go through the go gauge, but it won't go through the no go gauge. The no go means if the diameter of the pin is 10.1, it won't go into the 10.2 wide gauge. Okay? And that means it'll fail. I'm sorry, if it's too small, it will go into the no-go gauge. And that means that the diameter is too small and it's below 10.2. So these are the way go and no-go gauges work. And here's some more drawings of them. We're going to skip those. This is an example of a functional gauge. And a functional gauge is used on a part that's got multiple holes. And this is a part that goes into a fixture of sorts, and the pin replicates the hole. Not just the hole, but the hole at its worst case or virtual condition. So we need to understand a little bit more about that, and here's what it looks like. So what we have two things going on here. This is a pretty busy slide. First of all, this is composite position tolerance. And composite position tolerance has dual position tolerance requirements. And it's read position within a diameter of 0.8 millimeters at MMC to datums A, B, and C. And at the same time, a diameter of 0.2 millimeters at MMC to datums A and B, but not C. So really what we're saying here is the most important feature on this part is the pattern of holes. Okay? The pattern of holes from hole to hole is really, really important. It's got to be within a diameter of 0.2 millimeters at MMC to datums A and B. That's the most important thing on this part. Now, to make it easier to manufacture, we're going to allow that pattern of holes to float to datums A, B, and C now to a much greater degree to make the cost of producing those holes to the edges, the datums A, B, and C, more economical. And so this is why we use composite position tolerance. And that's what it is, how it looks, and why we use it. When we have it on a drawing, now, because the position tolerances are at MMC, I can use functional gauges. But before I use functional gauges, I have to measure the diameter of all these holes. And the reason that I have to do is because, remember, I have to always measure size and location. My functional gauge only gives me location. It never gives me size. So we have to measure size, and we can do it with a go, no-go gauge, or we can use an inside diameter micrometer or a caliper, or we have to use something to check that size. And we do that first for another reason. Anytime we have position tolerance at MMC, we get bonus tolerance. And bonus tolerance is calculated as the deviation from MMC to or toward the actual real hole size. And if the hole size is 12.2, then we get 6/10 of bonus tolerance on the one hole that measured 12.2. And so we got to know our deviation from MMC by checking size for two purposes. Number one, to check the box that said we check size. And number two, because we're checking for what the bonus tolerance is, so I can figure out what my CMM is going to do when we measure it. Because the CMM is going to figure out your bonus tolerance automatically. But if you're not using a CMM, you have to do it longhand. Okay, so we talked about composite, bonus tolerance, functional gauge, go, no-go gauge. The first functional gauge is in the lower left corner. And notice it is locating against the three datums. We got a simulated datum A, B, and C, and we have pins. But the pins are using the hole size at its MMC minus its position tolerance of 8/10. And so you see this pin, these four pins are a pin size of 11.2, even though the smallest hole is 12.0. We have to use the gauge to figure out the smallest hole or the biggest hole and its worst case allowable position error, which in this case is 8/10. I took it right from the feature control frame, right up here. Okay, so you take the MMC of the hole, 12.0, smallest hole, minus the 0.8, that gives me a pin size of 11.2, and that's the size that the pins have to be to check the position within a diameter of 0.8 at MMC. But in order to check the other position tolerance of 0.2 millimeters to datums A and B, we have a different pin size that is taken from the lower feature control frame, which is, I'm telling you where the math comes from, it's the MMC of the hole, which was 12.0, minus the 0.2, which is 11.8. And that's the diameter of all four of those pins. And so this is a functional gauge, what it looks like, how it's used, how we determine the pin sizes, and how it's applied to a part with composite position tolerance. Moving on, this is circularity and roundness inspection on a CMM. There are two ways to measure circularity and roundness. We can do it in an open setup with a dial indicator on a part that we rotate, and we don't get what's on the left. We get what's on the we get what's on the left. But if we use the same part and we put it on a CMM and we digitize points all the way around the part, we get all of these points. And when we hit enter into our CMM, the CMM uses a process called the sum of the squares, and it figures out what the roundness and the circularity is of all the points you gave it, and it will give you an accept or a reject, a good or a bad. And these two measuring processes give you different results. If you check something that was using the CMM on the right, and the CMM said it was acceptable, but you took it and you put it under not a micrometer, a dial indicator and you rotated the part, you would be measuring the travel of the dial indicator. You may get some points that are going to say they were out of tolerance that the CMM said using the sum of the squares in the algorithm of the CMM. The CMM said it was okay, but the dial indicator is going to say it's not okay. So you need to be aware that you could get two different things measuring the same part two different ways. So beware. More of the same thing. Simultaneous requirement is pretty straightforward. It is that we have a part with 5 holes in it. The datum the datum B is the center hole, and we have 2 patterns of holes located to that hole, and then we got the OD that's located to that hole as well. Now, the 2 patterns of holes that are circled in blue are measuring, they have a call out of position tolerance within a diameter at MMC to datum A and to datum B at MMC, and both patterns of holes are identical in the fact that they use maximum material condition in the feature control frame, and they use datum A as primary and datum B at MMC as secondary. And even though each of those 2 feature control frames have different position tolerances in them, one has 0.5, the other one has 0.3, they are interpreted as one pattern of holes. Okay? That means they don't float independently of each other. That means when we inspect these holes, we use one setup, we figure out where datum A is, datum B is, and we check pattern, the one pattern on the bottom and the one pattern at the top, and they both have to be located back to datum A and B within their own pattern requirement, but they're not 2 separate patterns, they're one. Now, why is that important? Because when we're building an assembly with 4 or 5 different parts on them that have different patterns of holes on them, a part like this, if they have 2 different patterns of holes that are not located to the same datums in the same order of precedence, then when we do a tolerance stack up, we have to build in additional clearance, float, and slop for these 2 patterns of holes on this one part. Whereas because I've located them as a simultaneous pattern, I don't have to add in additional float and slop and clearance in my assembly when I build my assembly up. Okay? So this is very valuable when you're doing a tolerance analysis or a tolerance stack up. Average diameter. Average diameter is, this came right out of the ASME standard. This is our acknowledgement that we use this graphic from there. The textbook that I told you about, the Krulikowski book, is very good, very thorough, but it doesn't have everything that's in the standard in it. And this is something that I found was important. I think it's important. I threw it into this. And that is, when you have a part that's real thin wall, like this part up here, and it tends to go out around, it's not well supported, and gravity makes it go out around, and in a free state, it's never round. It always is a little bit out around, but it'll still work. We can apply a call out like this that says average diameters within or between 1195 to 1200 with a roundness of 10 millimeters will work. And what that means is you have to take multiple measurements on the part in different or clock positions around here and do your calculations to calculate the average diameter of the 2 offsetting 90-degree measurements. And as long as they are within the drawing call out, the average diameters, these other extreme dimensions are allowed to be out. So it's a good tool. It's a nice thing to know is out there. It's another tool in your tool belt. Dynamic profile. We have normal profile, which means profile has to be normal to the surface. which is perpendicular to the curve. Okay, dynamic profile is a different thing. Dynamic profile is an application like this where we have composite profile being applied to some cutout like this. Now, dynamic profile means that we have two profile callouts. We have the 2 millimeter tolerant zone all the way around using that true exact profile, and it's allowed to float the actual surface of this cutout is allowed to float anywhere within this 2 millimeter tolerant zone. And if it does, it's acceptable. Then we also have this refinement of 4/10 of a millimeter, and it's allowed to float anywhere within that same 2 millimeter call out because of the dynamic symbol that we put on there. That little triangle allows it to float outside the 2 millimeter, and that's the big difference. Without that dynamic call out, this 4/10 of a millimeter has to be within the 4/10. With the dynamic, it can float anywhere in there. That's right out of the ASME standard. Primary datum shift. I got a couple of really difficult things here. Primary datum shift is we have a material condition modifier, very, very important, and it's a feature of size. I'm going to show you what it looks like. Here's my part. I have a position tolerance at MMC. I have a diameter. And what this says is, I'm going to go to the next graphic. Hang on, it's real complicated. It's the same drawing with more stuff on it. Okay, here's my diameter. Here's my position tolerance. My position tolerance out of the feature control frame is 1 millimeter. I get a bonus tolerance because it's at MMC. I get a bonus tolerance of 0.4 from my deviation from MMC toward LMC. So that 4/10 is that. And then I have a possible datum feature shift with this tolerance. As this tolerance goes away from MMC toward LMC, I can pick up 6/10 of datum shift. And that goes right there. So that it goes right there. So that my total possible shift allowable is 2 millimeters. Not at MMC, only at LMC. The farther away I go from MMC, the more possible shift I get, okay? So I only get 2 millimeters of possible float at LMC. That's why you got to know your MMC, LMC terms. Now, there's a lot of stuff going on in here, but I've tried to simplify it with the graphic, okay? I don't have time to go much deeper into that because I got 2 more subjects. Datum shift applied to holes. Datum shift only applies to holes. It applies 2 ways. I'm going to let you look at the really complicated diagram. Datum shift is allowed to only the pattern of holes, okay? We have 2 things here. Datum shift only applies to the pattern of the holes, right there, versus the actual holes themselves. There's a big difference here. We're allowed to let the pattern of holes shift, but not any of the individual holes within the pattern. And that's the part that you really got to think about. You got to really look at the key words here and look at what is in this graphic, which is pretty simple and straightforward, but is really this is the same graphic. It explains a couple of things. Datum feature shift is permitted only to the location of the pattern of holes, not to the individual hole position location. Now, does the Krulikowski book have all the arrows and the colored boxes? No, they don't. Those are from me. It's my attempt to help you figure this out. Keep in mind, the takeaway is the upper left corner. Datum feature shift is permitted only to the pattern as a pattern, not to the individual hole locations. And if you think about it, the pattern of holes is only checked with a functional gauge, whereas the hole positions are checked with a CMM. So that might help you. It helped me. And this is the same thing. And the last thing, I only have a couple more minutes. It's pattern locating tolerance zone features, PLTZFs, and feature relating tolerance zone features called FRTZFs. Doesn't matter what you call them. It looks like this. We have a composite feature control frame. You see it circled in green. The top one is called a PLTZF. The bottom one is called the FRTZF. Okay, the top one is the red ones. The bottom one is called the blue ones. Okay, and you already know composite tolerances. And what it means is the top position tolerance of 1 millimeter creates tolerance zones that look like that. And the bottom one creates tolerance zones that are much smaller and look like that. Okay, so the question then becomes, how are they allowed to move? The takeaway here is the axes of both hole patterns must be within the same cylindrical tolerance zone. The axis of both patterns of holes have to be within the big tolerance zone. And that's shown additionally in the next chart. Same graphic, same exact graphic, only now we're showing them, let's see, maybe I did it. Yeah. Okay, so this is part 1, and this is what it would look like. This is part 2, where the holes are on the periphery, and we have composite position tolerance. We have PLTZFs and FRTZFs, and this is the pattern for the top geometric control. This is the pattern for the lower geometric control, and the next slide overlays them and says, I'm going to read the box. When the secondary datum is not contained in the lower FCF, actual feature axis of each hole pattern shall be simultaneously within both tolerance cylinders. So this should be enough to show you what it would look like. And I'm sure you're going to want to look for what the graphic really looks like, so you can dig deeper into it. I know I certainly have. And so this is part B. This is part C. Part C has the slot. See the thing up here? We're going to skip that because it's just about like the other one. And so it's an awful lot of stuff. And Rose, Angela, I think I'm done. I think we went over a couple of minutes, maybe just 1 minute. And if there's any questions, I'm willing to answer them if you guys want to summarize them.
Yep. So thank you all for joining today. We are close on time. There were a couple questions. If we want to go through a couple, and then we'll answer the rest as we through email. So many of you asked about the slides, and if you texted me through the Q&A, we will be sending the slides out by PDF if you want that. And there was one question, Mike, would you scan or take hits using a CMM for roundness or circularity?
I'm going to go to that slide. So there's two ways to check for roundness or circularity. And one is with a dial indicator. And a dial indicator is going to give you points around the part as the part rotates. And you can write the points down. You can set it up, collect point number 1, rotate 10 degrees, point number 2, another 10 degrees, point number 3, point number 4, or you can just watch the total variation of the travel of the dial indicator. That would give you this if you were to plot it. And if any of those points are outside of the total travel from the lowest to the highest point, the dial indicator is going to tell you it was out of tolerance. But if you're using a coordinate measuring machine like in the top to digitize points around the same part, the CMM is going to collect that point, plot that point, and then it's going to calculate, it's going to do a calculation, which is an algorithm using the sum of the squares of the locations of those points, and it's going to make a circle. And it's going to tell you if, even if some of the points are outside of that circle, if the circle is within the requirement, the calculated circle using the sum of the squares, if that calculated circle is within the tolerance of the feature control frame, it will say it's good, even though some of the points that it actually collected were out of tolerance. And you have to understand, when you use a CMM, you get this kind of stuff. And so the CMM is just chock full of algorithms that do nothing but calculate stuff that you think that you don't really know what it's doing. It's programmed with all these algorithms to do what it's supposed to go do. It doesn't do what you think it does all the time. So that's why I'm saying beware, because I've had a lot of people say, I had somebody check a roundness of a part using a CMM, and they said it was good, but I checked it with micrometers and it didn't look good, and we plotted the points, and the CMM said it was good, but I found it was bad. Can that happen? And the answer is yes, it can happen. So that's why you have to understand, when you plug data into a CMM. Now, I love CMMs. They're magical. They are wonderful. They are super. But you need to understand what you're getting out of a CMM, and too many people don't know. And this is just a little peek into one of the algorithms that they use. Next
Great,
question.
thanks, Mike. I think we're out of time, but we can circle back to anyone that we didn't get an answer to. Thank you all again for joining, and hope you have a great afternoon. Thanks, Mike.
Thank you.